the Mandelbrot set. It's the set of points that stays finite after transforming the complex plane recursively. The structure of the set is so complicated, yet there are repetitions of the general structure as we look closer in at the set. If you look closely, you can find little baby Mandelbrots inside of the Mandelbrot set. And yet, for all of its complexity, the set is still invariant under the simple transformation that made it. This is the beauty of invariance. So, we'll investigate the Cantor set. Specifically, let's take a look at how the set is constructed. From the first stage to the second, we see that the original set has its middle third removed. From the second to third stage, we see that the middle thirds of the two smaller subsets are removed. This form of iteration can be more readily expressed using mathematical formalism. The left-hand side denotes the next set in the sequence that approximates the Cantor set, and says it equals some kind of transformation applied to the previous set in the sequence. The first set of parentheses on the right-hand side shrinks the approximation by a third. The second set of parentheses shrinks the previous approximation and then moves it 2/3 of a unit to the right. The middle symbol represents the union operator. It essentially combines the two sets created by shrinking and translating it into one set. This new set is the next in the sequence of approximations to the Cantor set. Expressed in another way, the next approximation to the Cantor set is made by creating two new sets by applying two transformations to the current approximation, then combining them into one new set. Note that the initial set we start the sequence with looks nothing like the Cantor set. In general, many interesting sets can be made by recursively taking a union of transformations applied to a set. The Cantor set is only one example of this. What makes the finalized version of the Cantor set different from the approximations is that it is stable. In other words, applying our construction procedure doesn't produce a change in the set. It's invariant to the transformation. We call this property self-similarity, since the object is similar to transformations applied to itself. Of course, this can only happen when the number of iterations goes to infinity. This sequence of sets and the transformation applied to them make up a dynamical system. The final result, or the invariant object of the system, is only present after the system has evolved sufficiently, and is referred to the attractor of the dynamical system. An important property of attractors is that a large number of initial sets for the dynamical system evolve towards the same attractor. In other words, the basin of attraction is larger than the set that is the attractor for the dynamical system. Deterministic fractals are the attractors of dynamical systems. Attractors are called so because they are the final result for a large number of initial conditions. Sets are attracted towards becoming an attractor. For instance, setting the initial set to a picture of a horse picture still results in the dynamical system evolving towards the Cantor set, the attractor of the system. Now that we have a fair understanding of the invariances of these attractors, we'd like to see what happens inside the parts that make up the invariances. To do this, we need to recall the notion of measure. The measure of a set returns a number. It's generally some notion of size or volume that the measure returns. For instance, the measure of a line quantified by its Euclidean length is additive. In other words, the measure of its parts equals the measure of the whole. This can also be shown pictorially. So, these properties can also be mathematically expressed with set notation for self-similar sets. The measure of the object is equal to the sum of the measures for its parts. Given the measure of the object, an interesting thing to know would be the measure of the similitudes that make up the fractal. Once again, let's consider the Cantor set. If we take the measure to be Euclidean, the measure of the sequence approximating the attractor will be the Euclidean length of each approximation. We see that the measure of each of the similitudes is the same. We also see that the measure is decreasing as a function of the iteration. As we approach the attractor, the measure goes to 0. In other words, the length of the Cantor set is 0. It's important to note that the Euclidean measure is not the only kind of measure we have available. For instance, we can use a counting measure instead. We see that this measure counts the number of line segments at each step. At the second, there are 2. At the third, there are 4, etc. It's important to note that this measure increases towards infinity as the sequence approaches the Cantor set. Finally, we have a measure that stays finite for each member of the sequence. We see that the measure is uniform. In fact, it's the same measure we used in part 1 of this series to integrate over the Cantor set. Now, there exist other fractals besides the Cantor set. Consider the Sierpinski Triangle. This is one possible construction to create the set. If we take the Euclidean length measure of each of the iterates, we find that it goes to infinity as the system evolves towards the attractor. So the length of the Sierpinski Triangle is infinite. However, there is another method that can be used to construct the fractal. If we take the Euclidean area measure of each of the iterates, we find that it goes to 0 as the system evolves towards the attractor. This means that the Sierpinski Triangle has infinite length, but no area. So the measure of our fractal seems to be dependent on which dimension we use. If we use the one-dimensional measure, length, it's infinite. If we use the two-dimensional measure, area, it's 0. We'd like a generalization of the measure that can be used for the fractal, such that its measure is neither 0 nor infinity, but it's something finite. In fact, if this is what we desire, it might be fair to assume that the dimensionality of the Sierpinski Triangle has to be something between 1 and 2. So we can have something finite, since finite numbers lie between 0 and infinity. In fact, the Hastar Measure is the solution to our problem. It's defined to be the smallest possible sum of a collection of set diameters raised to the d power such that the union of the set covers our object. In simpler terms, our measure is defined to be the most efficient covering of an object, where efficiency is measured by the size of the sum. Consider the construction of the Cantor set again. We can take this Hastar measure of the approximations. For the second level, we have 2 times 1 over 3 to the power of d for the measure. We can then continue this indefinitely. Note that particular choices of d correspond to measures we've already encountered. For instance, setting d to 0 corresponds to using the counting measure. Setting d to 1 corresponds to using the one-dimensional Euclidean measure. Given this correspondence, we can expect that our measure will be finite for some suitable choice of d. Computing the measure, we obtain the value 2 to the power of n times 3 to the power of negative n times d. As n increases, the measure will become infinite if the terms inside the exponential sum are greater than 0. If the terms sum to less than 0, the measure will be 0. Only when the terms sum to something finite will the measure be a positive, non-zero number. In other words, when the stuff in the exponential goes to 0, the exponential of 0 is something that's finite. Solving for this case implies that d must be equal to the natural log of 2 over the natural log of 3. This implies that the Cantor set has a fractional dimensionality, since the measure is only finite non-zero for this value. This dimensionality is referred to as the Hastar Dimension, or Fractal Dimension. Using this value for the value of d in the Hastar Measure yields the measure we use for integration over the Cantor set. This certainly is validation we've been doing things right. With all this new information, we can tackle the problem of integrating over the Cantor set in a trivial manner. Since we know how the Cantor set is constructed, we can immediately equate both sides of the equation. Then we apply a change of variables to both of the right-hand side integrals. This results in new integrals. Note that the domain is also changed, just as in regular integration. Recalling the definition of Hastar Measure, we can note that the rescalings of the object results in a proportional rescaling of the measure raised to the dimensionality of the object. Combining this knowledge with our knowledge of how the transformations work gives us a new expression for our integral. We can combine this into a rescaled version of our integral and a constant term. From here, we can then move the integral on the right hand side to the left and simplify. Then we move the multiplication term back over. This gives a value of a half for the integral, much faster than the method previously presented. So, there was a lot of information presented in this video, so don't feel bad about rewatching or consulting other sources. If you like the video, you should know this is part of a series called Fractal Analysis, essentially calculus with fractals. Thanks for watching, and make sure to subscribe so you don't miss out on the next video.